Herkese merhabalar. Bugün yine TÜBİTAK Temel Bilimler Araştırma Enstitüsü'nün Astronomi ve Uzay Bilimleri seminer serisi kapsamında bir güzel bölüm daha gerçekleştirmek üzere bir araya gelmiş bulunmaktayız. Yaklaşık 1000 yıl önce Müslüman bilgin Abdülrahman el-Sufi çıplak gözle Andromeda galaksisini keşfetmiştir. Yaklaşık 500 yıl önce Timurlu Devleti'nin bilim aşığı hükümdarı Uluq Bey, gözlemsel astronominin en büyük şaheserini, yeni bir astronomi cedveli ve yıldız kataloğunu ortaya koymuştur. Yaklaşık 400 yıl önce teleskopu gökyüzüne yönelten Galilei, Jüpiter'in 4 uydusunu ve Venüs'ün fazlarını keşfederek daha önce kimsenin aklına gelmeyen bilgilere ulaşmıştır. Yaklaşık 150 yıl önce Maxwell elektromanyetik dalgaları keşfetmiş, öngörmüş ve ışığın bir elektromanyetik dalga olduğunu kanıtlamıştır. Yaklaşık 100 yıl önce Einstein uzay zamanın dokusundaki dalgalanmalardan kaynaklanan yeni bir radyasyon türünü, gravitasyonel veya kütleçekim dalgalarını öngörmüştür. Einstein'ın kendisinin de ifade ettiği gibi tamamen soyut düşüncenin ve saf matematiksel yapının bir ürünü olarak öngörülen gravitasyonel dalgalar günümüzde deneysel olarak keşfedilmiştir. Bu dalgaların keşfiyle evrenin gizemlerinin anlaşılması için yeni bir pencere açılmış, uygarlığın gelişim sürecinde yeni bir sayfa açılmıştır. Bugün son derece değerli bir bilim insanından ABD'deki Johns Hopkins Üniversitesi'nin profesörü Emanuele Berti'den gravitasyonel dalgaları dinleyeceğiz. Bu vesileyle ben hepinizi saygı ve sevgiyle selamlıyorum. Seminerimiz İngilizce olarak gerçekleştirileceğinden ben de İngilizce devam edeceğim. Hello everyone and good evening. It is my distinct pleasure and honor to let you know that this evening we have another wonderful session of the Astronomy and Space Sciences Seminar Series of TÜBİTAK Research Institute for Fundamental Sciences, with the participation of Professor Emanuele Berti from Johns Hopkins University of United States. Professor Emanuele Berti is a distinguished scientist and world-class expert of gravitational science. He has kindly agreed to join us for this seminar, and he is going to give a great talk under the title, Gravitational Wave Astronomy, Peering Deeper. Emanuele Berti received a PhD from the University of Rome, La Sapienza, in 2002. He held postdoctoral position at the Aristotle University of Thessaloniki, the Institut d'Astrophysique de Paris, Washington University in St. Louis, and Jet Propulsion Laboratory, JPL, at Caltech. He joined the faculty at the University of Mississippi in 2009, and he moved to Johns Hopkins University as professor in 2018. Professor Berti specializes in gravitational physics and gravitational wave astronomy. His research interests include the structure, stability, dynamics, and formation of black holes and neutron stars, gravitational wave signatures of modified theories of gravity, and physics beyond the standard model, and preparing for the challenge of detecting gravitational waves in space with LISA. Professor Berti is a fellow of the American Physical Society and of the International Society on General Relativity and Gravitation. He served on the chair line of the American Physical Society Division of Gravitational Physics, and he is currently president-elect of the International Society on General Relativity and Gravitation. He is also a divisional associated editor in gravitational physics for physical review letters, and a member of NASA's US LISA study team. Now, I want to thank once again Professor Berti for joining us today and invite him to begin his talk. Emanuele, very happy to have you.
As should be clear from the title of my talk, I will discuss what I consider some of the most interesting directions for the future of gravitational wave astronomy. And there were a couple of very interesting developments in the last year in this direction. The first is that the US project for a third generation gravitational wave observatory called Cosmic Explorer put out their Horizon study. It's a plan of the science that these third generation detectors are supposed to be doing, and it considers the possibility of different observatories being built and how to build a community around those future observatories. In Europe, there's a similar project called the Einstein telescope, which also recently met a very important milestone. In 2021, it was included as part of the roadmap of ESFRI, which is a very long acronym that I always have trouble remembering, but it's the European Research Infrastructure body that approved this project, and there's going to be some funding to push it forward. And in the mid-2030s, ESA also approved for launch LISA, which is a space-based gravitational wave detector that will complement the abilities of these ground-based detectors by extending them to lower frequencies. This is all very exciting because if you look at the situation right now, we are more or less here where I'm showing the solid black line. What you see here is a plot of the noise power spectral density of different gravitational wave detectors. The ones that you see here on the right are all ground-based, and they go from the first and second observing run on LIGO to the advanced LIGO design, which is shown here in black. And then what you see in red are the best detectors that we can build in the current facilities of LIGO. And in green and blue, you see different proposed designs for Cosmic Explorer and the Einstein telescope. So everything above these curves is detectable, roughly speaking, and any improvement of a factor of 10 in the sensitivity of these detectors corresponds to an improvement by a factor of 10 cube or 1,000 in the accessible volume. So every time you go down by a factor of 10 in one of these curves, the number of events that you can see increases by about a factor of 1,000. Over here on the left, what you see are different proposed designs for space-based detectors. And in the US and in Europe, of course, the main project here is LISA, but there are also proposed Chinese projects like Taiji and Tianqin that could join LISA in space. And of course, these projects probe a completely different window in gravitational wave frequency. What's important to note is that different frequencies mean that you are observing very different astrophysical systems, because roughly speaking, the frequency oscillation of the black hole that you form from the merger of two black holes scales with the inverse of the mass, as I show up here in the top right of this slide. So for the ground-based detectors in particular, like I said earlier, as we go from LIGO A+ to Voyager, which is the best facility we can build in current detectors, there's going to be a sensitive, pretty large improvement in the redshift out to which we can observe binaries. That's what you see in this plot. But with Cosmic Explorer and Einstein telescope, we really have a phase transition, the kind of observations that we can perform, because these observatories can basically see all the binaries merging everywhere in the universe. They have a horizon redshift that goes out to redshifts of about 100. LISA will probe a completely different frequency window, like I said before, and we'll also see different sources. The main sources are the mergers of massive black holes. Here you see 3 example waveforms for the merger of a 10 to the 7 solar mass binary system, 10 to the 6 and 10 to the 5. And all of these will be seen with very, very large signal to noise ratios. Down here, you see the so-called extreme mass ratio in spirals. These are systems where you have a small black hole or a neutron star falling into a larger massive black hole like the ones that I'm discussing over here. And also, interestingly, LISA could observe multi-band binaries, systems like the ones that LIGO has already seen, that will start there in spiral at low frequencies and eventually merge in the ground-based detector sensitivity window. So this idea of having multi-band sources was first proposed by Alberto Cesana in a paper in 2016. What Alberto was thinking about at the time was the possibility of observing a GW150914-like source, the very first system that we have seen, as it first in spirals in LISA and then eventually emerges in the LIGO band. But because of the sensitivity improvements that I discussed earlier, what we should really be thinking about is the complementarity of detectors like LISA, for which you see the detection horizon over here, with detectors of the Einstein telescope or cosmic explorer class. So here, for example, you see the observability horizon for the Einstein telescope. And it's clear that there is a very large window of opportunity here at masses between, let's say, 10 to the 2 and 10 to the 4, where we could see many systems that are usually classified as intermediate mass black holes that could start there in spiral in LISA and merge in the LIGO, Virgo, Cosmic Explorer, Einstein telescope band. Now, with all of this increasing sensitivity, there's a lot of different exciting science that we can do. And this science was collected, as I said before, in the Cosmic Explorer Horizon study, where it was roughly classified in 3 different classes. First of all, we're going to learn more astrophysics. We will learn about black holes and neutron stars throughout cosmic time by observing many more merging binary systems and so characterizing their population, by looking at massive black hole seeds and therefore clarifying the way that galaxies form as well. And possibly, since the redshift horizon of these systems is so large, we could observe binary black holes that were formed from the collapse of the first star, so-called population 3 stars. Other interesting physics that we can do, but I will not discuss it very much, is understanding the dynamics of dense matter, because when you start seeing many binary neutron star mergers, you can also clarify the connection between these mergers and other high energy astrophysical phenomena like gamma ray bursts, kilonovae, nucleosynthesis, and phase transitions in the matter that makes up these objects. And very interestingly, and this is something I will discuss later on, we can study extreme gravity and fundamental physics, because with these objects, we could shed light on the nature of dark matter and dark energy, perform better tests of general relativity, and perhaps even discover compact objects that we did not imagine so far. So all of these topics, of course, are way too much for a talk like the one that I'm giving here. In fact, recently we organized a whole workshop, PAX 7, where PAX stands for Physics and Astrophysics at the Extreme, where we discussed all of these different science cases for 3rd generation detectors. And if you are interested, I invite you to just Google the workshop and you will see that all of the talks are recorded and available. Now, what I want to tell you is, first of all, I will give a brief overview of the main lessons we have learned so far from the LIGO and Virgo detections. And then in the rest of the talk, I will discuss what I consider the most interesting prospects for gravitational wave astrophysics and for tests of general relativity and fundamental physics with the next generation of detectors. First of all, as you probably know, LIGO and Virgo started their observations in September of 2015. Within a couple of days, we had the first historical detection of a binary black hole merger on September 14. And during the first observing run, LIGO and Virgo detected 3 black hole systems. Later on, what you see here is the sensitivity of the 2 detectors in the US, Livingston and Hanford. In August of 2017, these 2 detectors were joined by the Italian-French detector Virgo, and within a month, the number of detected systems almost doubled. In fact, here you see a pretty plot of all of the observed systems. What you see here is the frequency of the waves increasing as a function of time. And down here, you see the waveforms for many of the observed systems. As you probably know, they are classified by the detection date. And what you see here is that about half of them were detected in August when we had 3 detectors available. The first such detection with 3 detectors was the first system that we could localize in the sky. It was a binary black hole system. And the most notable of these detections in August was, of course, a binary neutron star system 170817, for which we also observed all sorts of electromagnetic counterparts ranging from radio to gamma rays. Now, from this first set of detections, we learned several things. First of all, we learned that the binary black holes that we detect have a certain mass spectrum. What you see up here, this figure is taken from one of the LIGO papers, is the rate of detected events as a function of the mass of the primary in the binary system. And down here, you see the same rate as a function of the mass ratio. Focus on the plot at the top. What you see is that quite independently of the models that the LIGO-Virgo collaboration used, they concluded that the observed binary black holes should have a cutoff up here around 40 or 50 solar masses for the primary mass. Now, this is very interesting because the theory of stellar collapse predicts that it should not be possible to form black holes from stellar collapse, which have a mass between about 50 and 130 solar masses. This is because of the so-called perinstability supernova or pulsational perinstability supernova, where what happens is that for stars so massive, you can have the production of electron-positron pairs, which deplete the pressure inside the star, and therefore all the matter collapses and bounces, and instead of giving rise to a black hole, you just eject a lot of matter. So the second conclusion that was quite surprising from these events is that there is a certain combination of the spin parameters that LIGO can measure more accurately. It's called the effective spin. And it's basically the mass-weighted product of the projection of the spins onto the direction of the orbital angular momentum of the binary. So basically this quantity is m1 spin 1 plus m2 spin 2 divided by the total mass. And most of the detections by the first 2 observing runs of LIGO pointed to this chi-effective quantity being compatible with 0. Let me point out that this doesn't mean that the spins of the black holes were compatible with 0. It could mean that the 2 spins are pointing up and down, or that they are oriented in the orbital plane, or all sorts of possible different combinations. But it was still quite surprising that this chi-effective was, for most events, not all of them, notice these 2, compatible with 0. In fact, as often happens, once you have an observation, there's a lot of theorists who can explain it. And there were papers in particular, these papers by Jim Fuller at Caltech and Ma, where they proposed as an explanation the fact that if you have collapse of stars, because of the way angular momentum transfer works in the collapse, you would end up with black holes that are spinning very slowly. And there is also observational evidence in favor of this, in particular in this paper by Will Farr and collaborators at Flatiron Institute here. They noticed that if you take all of the LIGO events and you put them together, you do have evidence for the population as a whole that the effective spin should have 0 mean with a relatively small variance. So there is both theoretical and observational evidence that the spins might be small. Now, this picture has already changed a little bit because during the 3rd observing run of LIGO, LIGO so far has announced only the first half of the events, bringing the total detections up to about 50. And there's about as many events which have not been published yet. So far, LIGO has published some of the most notable, in particular, the first detection of neutron star black hole systems. Anyway, the new detections, which have been made possible by an increase in sensitivity, have slightly changed this picture in various ways. Let me point out that we are still at the very early stages of gravitational wave astronomy. This is a plot from a paper that we wrote with one of my students, Vishal Baibab, and what you see here is the expected size of the catalog of binary black hole mergers over here, or binary neutron star and neutron star black hole systems as a function of time. And what you see is that as we go from O3 to design sensitivity and then better and better detectors such as Voyager, the number of events that we will see will go from the 50, maybe 100 that we have seen so far, up to something like 10 to the 4, 10 to the 5. So we will really enter an era of big data in gravitational wave astronomy. With the 50 events that we have observed so far, we have learned a lot of interesting things. Here I'm showing the mass ratio and total mass of the events reported in the O3A catalog. Some of these are particularly interesting. One was a heavy neutron star merger, heavier than what we expected from X-ray observations in the galaxy. And two other events were particularly interesting because they had a mass ratio that is very far from 1. This event had a mass ratio of about 3, and this other event had a mass ratio of 10, with the lower mass system in the binary having a mass of 2.6 solar masses. So we don't know if it's the lightest black hole ever detected or perhaps the heaviest neutron star ever detected. But even more interestingly, there is one event over here which fills the mass gap. So if you remember the plot I was showing you a little while ago, we did not expect to see any binaries with masses of the components larger than 50. And for this particular event, at least one of the two black holes must have a mass which is larger than 50. So of course, when you have these events, they challenge the expected astrophysical formation channels that were proposed. The physical formation channels that astrophysicists have proposed so far can be roughly classified in 3 classes. In one, you have star formation in the field, binary formation in the field, where you start from 2 stars, which undergo collapse one after the other, and through some mechanism that brings the binary components together, eventually merge and are observed in the LIGO band. The second formation mechanism is dynamical. Here you invoke the possibility that these compact objects are formed in very dense stellar environments, like globular clusters or young open star clusters or nuclear star clusters. And then because they meet very often, the meetings between these objects tend to eject the lighter ones and harden the heavier black holes in the binary until eventually you end up with a merger that is observed in LIGO. And then there are more exotic channels, for example, primordial black holes that can also produce a perhaps significant fraction of the events that we are observing. So these channels were collected together in a very nice review by Ilya Mandel and Florberg Garden. What you see here are the measured rates by LIGO and the rates that were predicted theoretically by different formation channels: isolated binary evolution, clusters, population 3 stars, and so on. And on the right, you see the same predictions for binary neutron stars. Now, what I want to point out is that the rates that you see in this plot are local rates. By that, I mean they are the rates of binary events measured at redshift 0, where we are. But what is interesting is that with next generation detectors, we will be able, as I say in the title of this talk, to peer deeper. In particular, what we want to understand is, does the rate evolution evolve with redshift? For now, we are observing the nearby universe, and it's very hard to tell whether the rate that we observe is constant as a function of redshift or perhaps increases. This plot is taken from one of the early LIGO papers. Another thing that has emerged from the O3 catalog is that the structure of the mass spectrum is actually more complicated than the one that I've shown you earlier. Now, the best fit model is what they call a power law plus peak, where you have a power law component with a peak in the middle. And this peak, interestingly, is at masses of about 40 solar masses, where you would expect the peri-instability supernova mechanism to play a role. So this plot is suggestive of the possibility that there may be more than one formation channel at work. And what we are observing with LIGO is a collective population that comes from different formation channels. So the interesting possibility now is to tell which formation channels are at work. One possibility to fill the upper mass gap that we proposed with Davide Gerosa, but the idea goes back to other papers by Cole Miller and others, for example, is that you could have repeated mergers. The idea is the following. Suppose that you start from black holes that are born from stellar collapse. The simplest possibility is that these two black holes, which are formed from stellar collapse, merge with each other and form one of the binaries that we see in light. However, it's also possible that you start from black holes that are formed from collapse, they merge once, this new merger remnant is going to be in the mass gap, and then this second generation black hole merges again with a black hole formed from stellar collapse, forming what we call a 1G plus 2G event, first generation and second generation together. Now, if this is what happens, of course, you also have the possibility of having multiple second generation mergers, which is what you see over here. If there is a multiple generation merger, general relativity tells us that when you merge two black holes that had 0 spin, you form a final black hole that has a spin of about 0.7. Besides, general relativity tells us that whenever the merging black holes have unequal masses or non-zero spins, they also receive a gravitational recoil. This is because the emission of gravitational waves happens preferentially in a certain direction, and by conservation of momentum, your binary has to recoil in the opposite direction. So these simple facts can be used to constrain the formation environment of the black holes. This is because if your black holes all had 0 spin, as you would expect if Jim Fuller and company were right, then when you merge two black holes that have 0 spin, you can get at most a recoil velocity that is of order of about 100, 200. But if you merge first generation and second generation black holes, then the typical recoils that you can get can be as large as a few thousands. And if you look at the escape velocity from galaxies or clusters, galaxies can retain black holes with recoils as large as perhaps 1,000 kilometers per second, but clusters can only retain black holes if their escape velocities are significantly smaller than 100 kilometers per second. So when you look at these distributions, it's clear that if the black holes that are in the mass gap were produced by multiple generation mergers, then it's quite unlikely that they were produced in clusters. In fact, you can quantify this by asking the question, if we see one black hole in 50, as we have, which is in the mass gap, and this black hole was formed hierarchically, what's the escape velocity that can support such a fraction of observed black holes? And you end up with a very interesting answer. That probability of retaining the black holes in clusters implies that the escape velocity has to be smaller than about 50 or 100 kilometers per second, depending on assumptions on the pairing of black holes that I don't have time to describe. So basically, if the black holes in the mass gap that we have seen were formed hierarchically, then most likely they were not formed in clusters. And this is the case for GW 190521, the mass gap event, for which, as you can see, it seems that you are really falling in that kind of phenomenology where one of the spins is of order 0.7 perhaps. And so this event could be hierarchical, but then if it is, it should not have formed in a cluster. Perhaps it formed in an AGN or some other astrophysical environment. You can push this idea even further. You can say, if Jim Fuller is right, not only we need multiple generation mergers to fill the mass gap, but in first generation mergers, we should always have very small spins and therefore small effective spins, which is what we observe. So if we start seeing black holes with spins larger than the maximum allowed by stellar collapse, those spins must have been produced by multiple generation mergers, maybe 2G plus 1G or 2G plus 2G. Then what you can do is take some astrophysical model, predict the gap, what we call the gap filling efficiency, the fraction of cluster events that can put black holes either in the mass gap or in the spin gap. And then you can use these theoretical predictions to determine, interestingly, the fraction of black holes that were formed in clusters relative to the total fraction of black holes. The idea works in this way. Assume that the 1G plus 1G channel is dominant. From the 1G plus 1G population, you can infer the value of Chimax. Let's say Chimax is the maximum spin of individual black holes formed in collapse is 0.1, for example. Then you can go here and you can take the chosen value of Chimax, and from your astrophysical model, you can get the efficiency of populating either the mass gap, which you see in red, or the spin gap, which you see in blue. And from that efficiency, by just algebra, you can get the number of events that were formed in clusters, and therefore the fraction of events that were formed in clusters relative to the total number of events. Of course, this scenario is oversimplified, but it gives you an idea of the kind of games that we could be able to play as the number of observations increases and we have more statistics and better observations. Another question that we asked recently is, it looks likely at this point that there are multiple formation channels at play. The most complete collection of astrophysical formation channels was compiled by Mike Zevin and collaborators in this paper. And what we said was, suppose that we take the astrophysical formation channels that are out there and we ask the question, is there still room for a fraction of the LIGO events to have been produced through the primordial black hole channel? So what you see here are corner plots that show you the fraction of events that were formed in globular clusters or common envelope evolution versus the fraction of events that were formed through the primordial black hole channel. And what is interesting, here you see the marginalized version of these contour plots, is that when you include only common envelope, globular clusters, and primordial black holes, you always end up with a fraction of primordial black holes, which is shown in blue here, which is around 0.3. So if you only include common envelope and globular clusters, there's still the possibility that 1/3 of the events in LIGO formed from primordial black holes. Then we tried to kill this conclusion because, of course, it would be shocking if that's true. And we tried to add other channels, nuclear star clusters. This is a stable mass transfer channel. I don't have the time to describe all of this, I'm sorry. But the basic conclusion is that in most cases, you end up with a primordial black hole fraction that excludes 0. The one case where the primordial black hole fraction is compatible with 0 is the one where we include stable mass transfer. And the reason you can see from this plot here, you see the mass distribution of the different channels, common envelope, globular clusters, nuclear star clusters, primordial black holes, and so on. And you see that if we do not include the stable mass transfer channel, then primordial black holes are needed to reproduce the observed mass distribution down here. While if we do include stable mass transfer, then the two channels are competitive here, and you mainly need the primordial black holes to explain events in the mass gap, which are unaccounted for by the models in the Zevin et al. Paper. The bottom line of these two slides is, I don't claim that we had detected primordial black holes, far from me, but the current uncertainties in astrophysical models still allow for the possibility that fraction of events in LIGO might be primordial in origin. Now, if we really want to test this idea, we'd better be able to observe binaries at large redshifts. And the reason is illustrated in this nice plot by Ken Ng at MIT, and this is a paper that he wrote with Salvo Vitale and others. What you see here is the expected distribution of binaries formed in the field and in clusters. This distribution is typically expected to peak at redshifts of about 2, where the star formation rate peaks, and then die out at larger redshifts. However, it's possible that black holes were formed by other mechanisms. For example, as I said earlier, from the collapse of population 3 stars in the early universe. In this case, the distribution of events should peak at much larger redshifts. Now, unfortunately, even with the best detectors that you can build in the current LIGO facilities, you're limited to redshifts of about 7. And so you will never be able to probe the population 3 the population 3 contribution to the total population of detected events, or whether some of the events are primordial in origin. And if you really want to understand what's happening at redshifts larger than about 7 or so, you need detectors like Cosmic Explorer or the Einstein telescope. Now, one problem is that if you see events that are at such large redshift, it's possible that you're going to see them, but at relatively low signal-to-noise ratio. And then you may observe them, but you may not be able to determine the redshifts at which they are. So perhaps you're seeing an event that is happening at redshift 10, but you will never be able to tell that it's happening at redshift 10. In this other paper, Ken and collaborators tried to quantify precisely that, and they came to the conclusion that there are some binaries for which the mass and the orientation are such that you could perform these redshift measurements and perhaps tell whether these black holes that you see are primordial or they come from population 3 stars. So this is all I wanted to say about astrophysics. Now I'm going to tell you something about what we can tell about general relativity and fundamental physics with next generation detectors. One of the ideas that have been explored in the past few years is the following. We know that in general relativity, the gravitational wave amplitude as a function of frequency can be written as it's a complex number, and it can be written as some amplitude times some phase. The amplitude and the phase in general relativity can be computed in principle with infinite precision. Now, assume that you have some theory of gravity that is beyond general relativity. This modified theory of gravity typically will introduce modifications in both the amplitude and the phase, and you can write them down as a post-Newtonian expansion in the velocity of the binary. The dominant contribution from any theory of gravity that you want to select will have some power b in the phasing and in the amplitude that are characteristic of the theory that you want to propose. So what you can do is say, well, okay, general relativity makes a definite prediction for the coefficients of the post-Newtonian expansion of the phasing. I can measure these numbers in LIGO, and I can ask whether they are consistent with the prediction of general relativity. If they are, I will obtain some measurement in the deviation of those parameters that has to be consistent with 0. This is something LIGO has already done, and they found bounds that get worse as you go to higher and higher post-Newtonian orders, because higher and higher post-Newtonian contributions are harder to measure. But so far, everything has been consistent with GR. So you can ask, as we build better and better detectors, how well can I constrain all of these post-Newtonian coefficients? And therefore, what kind of bounds can I put on these so-called parameterized post-Einstein parameters that tell me that there is some modification to GR that appears at a certain post-Newtonian order? This is exactly what we asked in this paper with Nico Younes and his student Scott Perkins. What we did was we explored 3 different scenarios. In one scenario, we do not get any third generation detector, and all we do is we build the best possible detectors in the current LIGO facilities, and at some point in the mid-2030s, these detectors are joined by LISA. In the second scenario, we build 1 third generation detector only, and in the third and most optimistic scenario, we build 2 third generation detectors. Then what we asked is, depending on these scenarios, 1, 2, and 3, as you see here, 1, 2, and 3, what am I gonna get in terms of the number of events that I observe, the signal to noise ratio of the events that I observe, and the number of multi-band systems that I can observe both in LISA and LIGO. All of this is summarized in this plot. Up here, you see the rate of events, which improves over time because your detectors are getting better. Here, you see the cumulative number of sources that are observed on the ground. This is similar to the plot that I've shown you at the beginning of my talk. And down here, you see the average log of the signal to noise ratio. So you start from signal to noise ratios that are just barely larger than unity. And then you end up with many events that have signal-to-noise ratios that approach hundreds. On the right, what you see are either massive black hole events that are observed only in LISA or multi-band events, the ones marked by MB, which are observed both in LISA and LIGO. Now, what you can ask at this point is, which of these populations of systems is going to give me the best bound on any given post-Newtonian coefficient? This plot has a lot of information. I don't expect you to digest it all now. But for example, you can focus on one specific contribution, say the one that corresponds to dipolar radiation. So if you look at any one of these plots, the typical trend is that the bounds that you place get better and better over time. And when you start including multi-band systems, sometimes the multi-band systems do much better than the terrestrial observations that you would be doing with LIGO. So for example, here, what you see is the term that would correspond to a -1 PN contribution, dipolar radiation. If such a term were present, you will be getting better and better with terrestrial detectors. But when you have multi-band systems, because you are seeing much lower frequencies, you're going to get much better bounds on negative post-Newtonian contributions. And so you will place much better bounds on theories that produce dipolar radiation. So the summary of the broad conclusions from this paper you can see here. Multi-band sources will be best to constrain negative PN orders, like dipolar radiation. Massive black hole systems are better than stellar origin black holes at negative post-Newtonian orders. That's because you can see them farther away. So the baseline for observing any deviation in propagation properties is larger. And also typically the coefficients that appear in the post-Newtonian expansion depend on powers of the mass. So that also helps you. If you are looking at terrestrial systems, these systems can still do better than LISA positive post-Newtonian orders. The main reason for this is that the curvature of stellar mass black holes is typically much larger than the curvature of supermassive black holes. And if you can make improvements in terrestrial detectors, those improvements are going to matter most when you want to constrain modified theories of gravity that give you modifications at negative post-Newtonian orders. I know that this discussion was rather technical. You can ask me questions, but the bottom line is the kind of theories of gravity that you can constrain with different detectors and different astrophysical systems, the kind of theories that you can constrain best depends on which particular theory you have in mind, what astrophysical system you have in mind, and what combination of detectors you're allowed to build given funding in the next few years. And then you can map all of these coefficients to specific theories of gravity, but I will not go into that. I want to tell you one last thing. There have been claims recently that recent LIGO-Virgo detections can already be used to do black hole spectroscopy. Let me describe the idea very briefly here. The idea is that when you have two black holes that come together and merge, they form a remnant black hole, which we expect to be a Kerr black hole. Now, in general relativity, the oscillation frequencies of a Kerr black hole depend only on the mass and the spin of the black hole. Sometimes this is called the no-hair theorem. So the idea is that if you measure the frequency and the damping time of one of these oscillations, you can determine the mass and the spin of the black hole. Now, if you can measure even only one more quasi-normal frequency, the frequency and the damping time of another mode, then you can use that measurement to say that you are testing general relativity. There was a paper by Max Sisi and others, including Sol Teukowski, where they claimed that they had done precisely this. What you see here is the mass and the spin of the remnant black hole that you measure through the full in spiral merger and ring down waveform. And the contour in blue shows the mass and the spin that you infer by assuming that there is only one damped sinusoid in the post-merger signal. So what they claimed in this paper was that by including an additional damped sinusoid, they got a much better agreement with the mass and spin measured from the full waveform. And in fact, they also claim that the deviation of the frequency and damping time from the value expected in GR, which is marked with a 0 here, is consistent with 0. So this frequency and damping time of the overtone are consistent with 0. As you can tell from the plot on the right, the measurement errors on the overtone are very large. And we are revisiting this analysis right now. And all I can say at this point is that we think that there are many important assumptions that went into this claim. We had claimed earlier that you could only perform the spectroscopy tests with at least Voyager class detectors, because you really need a pretty large signal to noise ratio to confidently claim that you have detected an overtone in the ring down signal. Our conclusion was confirmed more recently by other studies. For example, this work by Cecilia Cirenti and their student Tota, where in fact they find that none of the LIGO events could be used to do spectroscopy. And it's even questionable whether many of the LIGO events could be used to do spectroscopy if you even had Cosmic Explorer. But be it as it may, what we can say is that if we're going to observe binary black hole mergers in LISA, because of the very high signal to noise ratios that I was talking about at the very beginning of this talk, any detection of a binary black hole merger in LISA will allow us also to detect the higher order modes and therefore tell with certainty that the final black hole that you produce is a Kerr black hole. For the moment, I think that conclusions in this direction are premature, and there will be a technical paper about this on the archive, hopefully soon, where we discuss the reasons why I would rather be conservative. I will leave you with the final slide with my take-home messages. The bottom line is that we have already made a lot of progress in our understanding of the astrophysics of binary black hole mergers from the first 50 or so LIGO detections. All we can say up to this point is that all of the observations that we have are compatible with GR, even though our observations don't have the large SNRs that we will need to make very confident claims. And the future is bright, because as we build better and better detectors, we will be able to constrain astrophysical formation channels and do tests of general relativity and modified theories of gravity that are going to get better and better. Thanks.
Thank you very much for this comprehensive and very exciting talk. So we can now pass, I guess, to questions. Please send us questions, or you may ask just by raising hand if you have some questions. So we have received some questions by email. So first of all, I want to ask you, send you these questions, Emanuele. Can I do this?
Sure.
So these questions came from Professor Göksel Daylan Esmer, who asks, what are differences between gravitational and electromagnetic waves?
Yeah, there are several important differences between electromagnetic and gravitational waves. Some of the main differences are that gravitational waves are produced by coherent motions of matter, and gravitational waves are extremely weak. Gravitational waves also have an important advantage relative to electromagnetic waves, that while with electromagnetic waves, typically we detect power, in the case of gravitational waves, what we detect are amplitudes of gravitational waves. So in any classical field theory, the amplitude of a field goes like 1 over the distance. So for gravitational waves, like I said at the very beginning of the talk, any improvement in sensitivity by a given factor means that we are observing R cube more, because what we detect is the amplitude and not the square of the amplitude, which corresponds to the energy. So the weakness of gravitational waves has been what has limited us for a very long time, and the reason why it took us 100 years to finally be able to detect them after their theoretical prediction. But now that we have detectors that are sensitive enough, relatively modest improvements in technology can increase the number of events that we see and their signal to noise by very large factors. So I hope this answers the question.
Yeah, thank you. So the next question is, do gravitational waves undergo bending like electromagnetic waves when passing near a massive object? Is it possible? Possible?
Yes, they do. And gravitational lensing is one of the most exciting prospects for the future that I did not describe here. Actually, one of the people in this audience is my student Mesut Çalışkan, who is working precisely on that. What we are trying to understand is whether the massive black hole systems that we will observe in LISA, which are very far away, can be lensed at significant rates that will be observable. There have been claims that some of the LIGO events are lensed. Those claims have been debunked by various people, including members of the LIGO scientific collaboration. But as the number of events that we see grows, and as we see farther and farther events, there will be some fraction of those events that are lensed. And this will be very exciting because it will allow us to understand something about the nature of the lenses.
Thank you. So the next question is somewhat continuation of the first one, I guess. Can one obtain the image of an object by means of gravitational waves, like in electromagnetic case?
I am not sure what you mean by obtaining the image of an object, because the image is something that is associated with electromagnetic waves by its own nature. But what you can do with gravitational waves is characterize in a very precise way systems that are not visible. And so what you want to do when you observe binary black hole mergers is precisely that. These are systems for which you cannot produce an image because there is no matter around them, but you can use your gravitational wave signals to understand precisely what produced the merger. And this is what we are already doing to some extent. So yeah, if you like to call that an image, usually people use the sound analogy because gravitational waves are emitted in the audio band. So you can see it as adding an additional sense on top of producing images.
Thank you. You mentioned about the mass of remnant black holes after merging. What is the maximum mass of a black hole inferred from the present observations of gravitational waves generated by merging?
Right.
How can it affect the existing theory of stellar evolution? You indeed talked about it, but question came nevertheless. Will you elaborate more on this?
Right. So the heaviest binary black hole system we have observed so far is 1905-21. This system produced a remnant that has a mass of about 150 solar masses. So if you define, the measurement is not particularly precise because the system was located very far away, and it has been interpreted in many different ways. I would say that we're not even sure that it's a binary black hole merger at all at this point, because the signal to noise ratio was not very large. Depending on the waveforms that you use to do the data analysis, you get very different values for the component masses, for the mass ratio, and so on. This is all an artifact of the fact that our detectors are not particularly sensitive to events that are very far away at the moment. But the system compensates because of the very large mass. So if you believe that it's a binary black hole, then this is the largest stellar mass object produced so far. the mass of the remnant being 150 solar masses does not constrain collapse scenarios, because that we believe was the result of a merger remnant. But what is interesting is that the mass of the primary component in the merging system was of the order of 80 solar masses. And if you look at the LIGO paper, it quite confidently excludes 50 solar masses. So if that is true, then it's quite likely that the primary component in the merging system was not produced by stellar collapse. This is the reason why I was talking about hierarchical mergers and where these mergers would occur, because it seems hard to make it by stellar collapse. Of course, after the claim that the system was not made by stellar collapse, people went back and revisited their assumptions for uncertainties on the location of the peri-instability supernova mass gap. And some people said, well, maybe we can push that limit up to 60 or 70 solar masses. Maybe there is accretion, maybe many things. But, you know, our current theories of formation of black holes by stellar collapse are strained, at the very least, by the existence of the system.
Thank you very much.
You're welcome.
What is your forecast for the detection of primordial gravitational waves generated during inflationary era as predicted by some models of the very early universe?
I am no expert on cosmological gravitational waves. My colleague here, Mark Kamionkowski, can tell you more about this. But my understanding is that there are very constraining upper limits on the tensor to scalar ratio. The most stringent upper limits come from BICEP. There was a paper that came out just 1 or 2 weeks ago constraining the tensor to scalar ratio. If you believe in standard models of inflation, then we think that soon we may be able to get to the point where you could rule out values of the tensor to scalar ratio that correspond to canonical models of inflation of the kind that we teach in textbooks right now. So I would say that within maybe a decade, we will be able, with things like pulsar timing arrays, to constrain cosmological background of stochastic gravitational waves to levels that become interesting.
Thank you. One more question. As for the modified theories of gravity, what do you think? Is it possible to measure the tidal love numbers of black holes or neutron stars by gravitational waves?
Neutron stars and gravitational waves are different beasts from this point of view, because we know that the tidal love numbers of neutron stars are non-zero also in general relativity. And it will be possible to measure the tidal love numbers on neutron stars as the sensitivity of our detectors improves. What you need there is really sensitivity at the lower end of the gravitational wave, ground-based gravitational wave detectors, because you would like to see many cycles of in spiral. And it's by detecting a long stretch of in spiral that you can measure the tidal deformability of neutron stars. From this point of view, detectors like Cosmic Explorer and the Einstein telescope should allow us to do a lot of interesting physics with neutron stars and constrain their equational state. For black holes, the issue is that in general relativity, the tidal love numbers of black holes are predicted to be exactly 0. And so there are many interesting things that one can do. If you see objects that cannot be neutron stars and you measure a non-zero tidal love number, then that's one of the possibilities that people have taken into account to say that perhaps we are observing an exotic object within general relativity, or perhaps general relativity is not correct at all. And there are many papers on this, forecasting what kinds of detectors you need to make such a measurement. And it's very interesting, and we will live and tell.
Thank you very much. And final questions, please, which states that you mentioned that observing deviation from GR depends on the specific nature of the modified theory, modified gravity. Which modification of general relativity provide more probable signal that can be observed in the existing or planned detectors?
And this is a very good question. And it also depends on the system that you want to observe. It's a very, this would be a whole other talk, but let's say the most popular modification of general relativity that has been studied since the late 50s is Brans-Dicke theory, or, you know, in modern incarnations, scalar tensor theories of gravity. Now people are talking about Hortensky theories and the degenerate higher order scalar tensor theories. These are all progenies of the original Brans-Dicke theory. In almost all of those theories, black holes are completely identical to the black holes of general relativity. So if you want to test all of those theories using black hole binary systems, you just can't, because the black hole solutions are the same. And even if you take black holes in a binary, they end up radiating away any excess scalar field and turning into the black hole solutions of GR very rapidly. So there are, let's say, generalized no-hair theorems that show you this cannot be done. But some classes of scalar tensor theories effectively evade the no-hair theorems that I just described. And one class that we have studied recently in several papers goes under the name of Einstein scalar Gauss-Bonnet gravity. In this class of theories, you couple the scalar field with the Gauss-Bonnet invariant, which is second order in the curvature in the action. These classes of theories allow for black hole solutions that have non-zero scalar charges. And then you produce dipolar radiations, and these are theories that you can constrain. Other theories that people have considered lately include dynamical Chern-Simons. Same story there. You can get black hole binaries with non-zero dipolar radiation. And yeah, so it depends. This question is complicated, and with neutron stars, even scalar tensor theories could produce interesting effects. The problem there is that we don't know the equational state of neutron stars well enough to do very precise tests of gravity, because our ignorance of the equational state is kind of degenerate with modifications due to modified gravity that you could think about.
Thank you very much. Thank you so much once again. And as a final remark, I would like to say that we will be very happy to see you in person after this COVID-19 disaster finally resolves in the world. So please welcome to visit us for our summer schools, or just for seminar, or just visitor, and to talk more about this very modern and exciting things.
Thank you so much for the invitation. I will be very happy to travel as soon as possible.
So if you don't mind, if you want to say something at the end, your final remarks, please, you're welcome to say.
I would just like to thank you again for inviting me, and yeah, I enjoyed giving the talk, and thanks a lot.
Thank you. That was excellent talk. So then we can stop here. What do you think?
Thank you. Bye.
Okay, we can stop here. Bye.